Continuing on with our discussion on the topic of motion along a straight line or kinematics, let's now go over the concept of constant acceleration. When the acceleration is constant at zero, the object is said to be undergoing uniform motion. On the other hand, when the acceleration is constant, but this time at a non-zero value, you have uniform acceleration. For uniform motion, the acceleration is constant at zero. The velocity is constant. The rate of change of velocity is equal to 0. The velocity is constant. As such, the equation for velocity reduces to simply delta x divided by delta t, or simply x over t. Change in position divided by change in time. And constant, the velocity is constant. Therefore, if you try to get the average velocity will also be equal to x over t. On the other hand, if you have uniform acceleration, the acceleration is constant at a non-zero value. You have four equations by which you may analyze the problem or situation. Again, we have v is equal to v naught plus at, x is equal to v naught t plus 1/2 at squared, v squared is equal to v naught squared plus 2ax, and v average is equal to v plus v naught divided by 2, the average of the final velocity and the initial velocity. V average is also equal to delta x over delta t, or simply x over t. V is final velocity, v naught is initial velocity, a is acceleration, t is change in time or elapsed time, and x is the displacement or delta x. So let's now go over a few sample problems, a few examples. Let's have sample problem number 1. You have a car, accelerates from 40 kilometers per hour to 100 kilometers per hour in 10 seconds. Assuming that the car accelerated uniformly, determine the acceleration of the car. Here, the problem tells us that the object is undergoing uniform acceleration. In other problems, the problem might simply say acceleration, and you would have to determine if the object is undergoing uniform acceleration or non-uniform acceleration. One big difference between the two is that for non-uniform acceleration, the problem itself will provide an equation that is describing the motion of the object. In this problem, you are being asked to get the acceleration of the car, but no equation is provided by the problem. So in all likelihood, this is uniform acceleration motion. And indeed, the problem tells us that the acceleration is uniform. So given the object accelerates from 40 kph to 100 kph, therefore this is initial speed, and 100 kilometers per hour is the final speed. If we give the speed or the magnitude of the velocity direction, we have the velocity vector. Now, the problem does not provide any directions, so we are free to assume the direction for the motion of the object. For simplicity, let's assume that the car is moving along the x-axis towards positive x direction. So that means initial velocity V naught is positive 40 kph. Convert to meters per second. It's always a good idea to convert your variables into MKS system, meter, kilometer, MKS, meter, kilogram, seconds. So that's MKS. So kilometers per hour, convert to meters per second. Final velocity is V is equal to positive 100 kph, convert to meters per second. And the elapsed time is 10 seconds. So T is equal to 10 seconds. We are being asked to determine the acceleration A. And we know A to be constant, uniform acceleration. Now for uniform acceleration, you have four equations to choose from. Again, going back to the previous slide, you have four equations to choose from using the first equation. Trying out the first equation, V is equal to V naught plus AT. V is equal to V naught plus AT. If you look at the known values, we know final velocity V, we know V naught, and we know T. The only unknown is acceleration. Isolating A and plotting in the known values, we are able to calculate the acceleration of the system. You have 1.667 meters per second. Next up, we have sample problem number 2. Starting from rest, a car travels 20 kilometers along a straight highway in 15 minutes. What is the final velocity of the car? So here, the object starts from rest. Therefore, initial velocity is equal to 0. The car travels along a straight line, straight highway, travels 20 kilometers. The displacement x, therefore, is equal to 20 kilometers. Convert to meters. And the elapsed time is 15 minutes. Convert to seconds. And we are being asked to determine the final velocity v. So again, you have accelerating system. The object starts from rest, but the object moves. Therefore, the velocity of the object changes. The object has acceleration. And since no problem or no equation rather is provided by the problem, this means this is uniform acceleration. So for uniform acceleration, once again, you have four equations to choose from. This time, if we look at the second equation in the list, x is equal to v naught t plus 1/2 at squared. Initial velocity is 0, therefore v naught t is just equal to 0, which means x is equal to 1/2 at squared. We know x, we know t, the only unknown is a, so isolating a, we are able to determine the acceleration of the object. 0.04938271605 meters per second squared. Now, we got acceleration, but the problem is asking for final velocity, so we are not yet done with our solution. So going back to the list of equations for uniform acceleration, you have three other equations to choose from. So looking at these three equations, We can try out the first one. V is equal to V naught plus A t. Once again, initial velocity is 0. Therefore, V is just equal to A t. Knowing t, and now that we know A, we are able to determine the final velocity of the object. 44.444 meters per second or 160.000 kilometers per hour. Next, we have the following sample problem. A man sees a car without a driver roll by and starts sprinting after it at a constant speed of 3 meters per second. The car has an initial speed of 5 meters per second and is decelerating. So we talked about this before. The object is decelerating at a constant rate of 0.5 meters per second squared. How long before the man catches up with the car? In this particular problem, you have two objects. In the previous two problems that we covered, only one object is being considered. Only one object is moving in a straight line. In this problem, we have two objects, the man and the car. So, we need to take into account the motion of these two objects. Now, when you're talking about analyzing the motion of two objects, it pays that you do the analysis separately, one object from the other object. Analyze one object as if the other object is not present, and then do the same thing for the other object. And then you can unite the two analyses using either X or T, as you will see in this particular problem, in the solution for this problem. So we have two objects, the man and the car. The man has a constant speed of 3 meters per second, constant speed, constant velocity. The problem does not provide any direction, so we are safe to assume the direction. So let's say that the man is moving in the positive x direction. The same goes for the car because the man is running after the car. So V man, the velocity of the man is positive 3 meters per second and it is constant. The car has an initial speed of 5 meters per second, therefore initial velocity of the car, V car initial is equal to positive 5 meters per second. The car is decelerating, therefore the acceleration, if the car is moving in the positive x direction, the car's acceleration is moving in the negative x direction. Therefore, a car is negative 0.5 meters per second squared, and the problem tells us that this is constant. So we have two objects moving. The man is undergoing constant velocity, therefore uniform motion, whereas the car is undergoing uniform acceleration, constant acceleration at a non-zero value. Since the man is running after the car, both the man and the car will have the same displacement and same time of travel. So we can use X and T to unite the two analyses that we will do. The analysis for the motion of the man and the analysis for the motion of the car. Starting with the motion of the man, uniform motion, therefore V is just equal to X over T. Isolating x is equal to v times t. Going now to the motion of the car. The car is undergoing uniform acceleration. You have 4 equations to choose from. One of those 4 equations is x is equal to v initial t plus 1 half a t squared. X, we can use x to unite the two analyses. Therefore, v man t is just equal to v car initial t plus 1 half a car t squared. Canceling out t or dividing the whole equation by t, we have v man is equal to v car 1 plus 1 half a car t. Diba? Divided by t, so cancel out yung t here, cancel out the t here, t squared divided by t will give you t. Only t is unknown. We know v man, we know v car initial, we know a car. The only unknown is t, so isolating t and plotting in the values, we are able to determine the time of travel, t. T is equal to 8.000 seconds. So again, when faced with a problem involving more than one object moving in the system, analyze each object in the system. So in this case, the man and the car. Analyze each object in the system separately from each other, and then you can use x and t to unite the two analyses. And that's it for now. We'll continue our discussion, motion along a straight line in the next video. In the next video, we'll take a look at non-uniform acceleration. So again, that's it for now. Thank you for watching.